Hi, welcome to Lab 2 Projectile Motion. My name is Mateo Jelenkovic, and this is Physics 2211. So, the overview of the lab, I'm going to introduce you to the lab. I'm going to show you the procedure for doing the lab, as well as the physics principles and equations used, and then the computational model code and results, and then the comparing the computational and experimental model, and then a discussion and a conclusion. So the purpose in doing this lab was observing the effects of gravity and drag on a computational versus experimental model. So one of our computational models will have drag included, and then one will have without drag. So the physics principles we used were gravity, drag force, and Newton's second law. So the procedure in doing this lab, we recorded a video of a tape roll being tossed in the air going up and down, and then we used Tracker to plot the results of that video, and then built a computational model with and without drag force to compare the two models, and then finally discuss it. So harping back on the physics principles, we had gravity, which is an attractive force that pulls objects together. Drag, which is a resistive force that opposes objects' movements, in this case air drag, and then Newton's second law, which is weight is proportional to how easy it is to move an object, and then change in momentum equals net force applied. So our equations were gravitational force equations, which is m times g, and then um, the outer space gravitational force equation as well. And then our drag force, which is negative b times the vector of velocity. And then obviously our velocity and position update formulas, as well as Newton's second law, which is change in p over change in t, which is change in momentum over change in time. So more on drag force, it's assumed in this case that drag will not matter, but drag will matter. It's going to be accounted for in this scenario. Matter of fact, there's always going to be drag, but because it's such a small toss, people think that drag wouldn't be applied, but it would be applied in this scenario as well. So our computational model code without drag force, we had the position vector, which we started at 0, 0, 0, and then our initial velocity, which was 4, 2, 0, which is 4 in the x direction, 2 in the y direction, 0, and then our frame rate of 0.0033 for a delta t, and then we had our position and velocity update formulas, as well as the F net for gravity. And then with drag force, we had the B, which is 0.005. And then we added as well some factors, including drag. And then had F net be force of gravity plus force of drag. And then you could see it in this picture here. It's pretty much like our video. And then this was our position computational model results. So it went about 1.65 in the x direction and about 0.62 in the y direction. And then velocity, it should be straight because it doesn't change much in the arc. So it's going to be a normal velocity straight down. And then these are results comparing the tracker to the glow script and the glow script with the drag. So these graphs basically line up identically, but have the inclusion of difference with the drag, as well as human error, which is what we're going to talk about now. So our possible sources of error were us miscalculating drag, that was that B value, or not tracking accurately or misthrowing the tape roll, which could have affected it as well. Hypotheticals, what if the experimental model reached terminal velocity? So drag and gravity forces would completely balance each other out and equal each other, but the graph would still look the same. And what if we took the tape through the tape roll in a different way? Position and velocity would still have the same shape, just different values overall. So our conclusion, the lab was successful because Newton's second law, gravity and drag models were all observed. and thank you.